So in this next lesson, we're going to switch gears a little bit, and we're going to talk about something called systems of equations. So we're going to remind ourselves what that is from previous classes you've taken, and we're going to look at it though in one simple context before we look at it in the others. You'll see what we mean by that as we continue along. So what exactly do we mean by a system of equations? Well, you'll notice here that I've got two separate equations, and I've connected those two equations with this curly bracket right here. By using that curly bracket, what I've done is I've said that these two equations are related to each other, that these x's here are the same and these y's right here are the same. Okay? So by connecting these two equations, I'm saying that they both belong to the same context. Now what I've done is I've graphed the bottom equation here that's in blue, and I've graphed the top equation here that's in red. Now we need to understand what the graph of an equation actually represents. The graph of an equation represents a collection of all possible coordinate points that work in the given equation. So any point along this red line will work if I plug it into the x and y coordinate of the red equation. Okay, so for instance, if I took this point right here and I found the x and the y coordinate of that point, I know that because that point is on the graph, that it will absolutely work in my equation. Now what if I pick a random point, like right here? Is this point on the graph of my equation? No. So we know that it won't work in there if I put the xy coordinate point from that equation into this, from the graph into that equation. It won't work. So the same is true with this blue equation. All of the points that lie on this line are points that work in that equation. So the question that we want to ask ourselves is there any x and y coordinate point, a single point that doesn't just work for one of the equations, but works for both of the equations? And graphically speaking, we can see that visually by simply looking at where do the two lines intersect, because that's the only location at which they share a point. And the points on a graph are the points that work in the equation. So this point right here should work in both. It looks like the coordinates of that point are 4, -1. Let's check that. For this top one here, if I do -1 in for y equals 3/4 times 4 minus 4. I know the 4 times 4 will go away, or 4/4 goes away and leaves the 3. So that's -1 is equal to 3 minus 4, which produces -1 equals -1. Check, it works. We've got that one done. Well, what about this other equation here? Let's plug in -1 for the y equals -5/4 times 4. That's the point we're working with, plus 4. -5/4 times 4, those cancel out. I'm left with -1 equals -5 plus 4. -1 equals, well, -5 plus 4 is -1. Again, a true statement. -1 does equal -1. So what I've done is I've verified that this point at which the two lines intersect actually does work in both equations at the same time. Any other point I could pick this point right here. This point right here would work in the red equation, but it wouldn't work in the blue because it's only a point that exists on the graph of the red, not the blue. There's only one point at which that happens, and it's that point that we found right there. So let's do a full example ourselves. We've got a new system of equations here. Here's my two equations. Y equals 4/3 x minus 2. Let's go ahead and graph that one. We remember that graphing linear equations, we go down to the y-intercept, which is -2. And then we use our slope of 4/3. So that means I go up 4 to the right 3. And there's my new point. Up 4 to the right 3. There's my other point. I'm going to go down 4 and to the left 3. down 4, and to the left 3, just to get several points here to make sure that I've got everything graphed as good as I can get it. Let's go ahead and do that with this next equation right here, the y equals negative 1/3 x plus 3. Okay, so start at the y-intercept of 3, and negative 1/3 means I go down 1, but I only apply the negative to the top, so I'm going to go to the right 3, down 1 to the right 3, down 1 to the right 3. So I've got several points I can connect here now, and the question from the previous slide was, what's the solution? And we saw that from the previous slide, the solution is the point at which the lines intersect. That right there is the only xy coordinate that is on both of the graphs. So what does it look like the coordinate is? 1, 2, 3, and 2. So it looks like the solution to this system of equations is the coordinate point 3, 2. So again, the solution is the point at which the two graphs intersect. That's the only xy coordinate point that will work in both equations. Verifying that really quick, bringing this one down, I've got y, which should be the 2, is equal to 4/3 times 3 minus 2. Is that true? 4/3 times 3 is 4. Does 2 equal 4 minus 2? Well, yeah, 2 does equal 2. Check, it works there. Let's check the second one. Plug 2 in for y, equals negative 1/3 times x, which is a 3, plus 3. Negative 1/3 over 3 is negative 1, or times 3 is negative 1. So 2 equals negative 1 plus 3. Negative 1 plus 3 is 2. Does 2 equal 2? Check, it works. So we see that that point at which the two lines intersect is the one coordinate point, xy coordinate point, that works in both equations.